Okay, so hello everyone. My name is Kian, and I will be the speaker of today's topic. And today I will present to everyone here about an interesting paper that have have been published quite a long time, but still one of the most innovative idea in the reinforcement learning field. And the topic of our our seminar today is about distributional reinforcement learning. Okay. Uh, and the content of our seminar today will briefly be concluded in three parts. The first part I will uh, it will be about some briefly introduction to reinforcement learning for for the audience who need a basic idea about what going on to be in this seminar. And the second part will be our main content of today is about the idea behind the distributional reinforcement learning. And the third part will be some algorithm that takes this idea. Okay, but in the first place, can I ask how many of you are in this meeting today have some idea about how reinforcement learning work? Does anyone? Okay, so I will take this part quite short. Okay, the the idea behind reinforcement learning is uh, to deploy an agent in the real in the real world situation or in the simulation. And the goal of the agent is to maximize the reward signal that come from its environment. And some concept in reinforcement learning they are the return GT here. The GT is defined as the future reward, and the GT is a summation of continuous reward in the future, not include the reward as the present. And and the uh, and the idea to in reinforcement learning, there another concept that you have to know is about the Markov decision process. Uh, the brief idea about Markov decision process is that uh, s- that it classify into state and time, like in all the process of how everything work. You can define uh, in at one moment that that time is t, and there some simple component like the state of how everything be there will be denote as st. And what action you will take with will be denoted as at. And the reward of the action that affects the state at that time t. And this chain will be uh, combined into a chain of t plus 1, t plus 2. And the problem that we need to solve in the reinforcement learning is that how can we maximize the rewards in all process from the moment of t to the big T, which will be denote for the terminal state, uh, the moment that every thing in the process will be end, or you can say that is an game over moment. Okay. Uh, so to solve the process, uh, the problem here many researchers uh, come come to the idea of using the expected returns. So they will they will the idea about expected return is you run the game from all process, like from moment t to the terminal state, and you will uh, calculate it backward, so you can have an overview of what the value of expected uh, of the return will be. And this formula is also can provide the value function. And from the idea, like from this idea, you will have the Bellman equation, which very familiar to most of everyone here. It will be denoted as Q with policy pi. Take one moment, like take the state S and action R to to and the output will be the value of the state with the action A. Oh, slide have some problem. Okay, so that is a basic idea of reinforcement learning that we will tackle the problem with the idea about the expected value. But not recently, in 2017, a paper of Mark Belgerman and Will Dabney about an interesting idea that instead of using the expected value of reward, they approach the problem with an distributional perspective of reinforcement learning. And this paper,
Uh, we cannot see your presentation.
okay, sorry for that. Everyone can see now. Okay.
Okay.
So the idea at that time is going again all the paper that tackle the reinforcement learning at that time. Like at that time, people approach the problem with some idea about is say you know network to approximate the Q function, the value function in reinforcement learning, or they introduce some backbone net architecture like arithmetic to improve the performance of reinforcement learning model. But the tackle the approach of Mark Belgman have an interesting idea that they come from the root that what if they don't use the expected value, they use all the distributional. Okay, so as I said, unlike the traditional reinforcement learning that focus on the expected value of return, distributional reinforcement learning model that will try to have an approximate the distribution of the return at that time. And this approach have some advantage that it will help to provide richer information and can improve the risk sensitivity. For for the clearer explanation of what distributional reinforcement learning can bring to improve the normal reinforcement learning problem, I will have this example. So everyone here knows the game Monopoly, right? You toss some dice and your piece will go in one of the square, and for each square you will gain or lose some money, or sometimes you just don't gain anything, right? For example here that we have an let's say a player or agent, and with and ahead of him is some square that if he toss m- number 2, he will go into the boardwalk square, which there is a hotel here. Then he will lose a lot of money. But on another hand, if he toss the die of any other value apart from 2, he will uh, escape from the uh, hotel, and he will gain $200. And if we tackle this example from a traditional reinforcement learning view, the expected value uh, of n the expected reward of this will be uh, 138, or nearly 139. And you can see that right here, uh, uh, there 36 possibility can happen. But if he uh, if he go in uh, any number apart from 2, he will gain a decent amount of money. But the possibility of going into board the boardwalk square is very low, despite of the heavy penalty of losing $2,000. And so the expected value here is still positive. But look on another hand, from another view, uh, this this approach will expected value will likely to equal the value if you go uh, uh, if you uh, go to on the road with without uh, any penalty, but you will gain a much smaller uh, reward than $200. So this example will show that uh, the agent will still take the action in this situation, because the possibility of losing money is very low here, which uh, which we sometime in reinforcement learning uh, the agent will take the risk to earn the higher value, or or they or he just don't care about the risk at all. And this approach can this this problem can be addressed by the distributional reinforcement learning that I have put in here. It improves the risk sensitivity. So to have an overview about how about what traditional about what distributional reinforcement learning work, we could move here. So the on okay. It's some simple explanation of that idea, but uh, I think I will interpret it in another way. So to make it clearer, in the traditional reinforcement learning, your agent only know about this number. It's only 138, right? He only knows the expected value, like he will uh, s- he will have the summation is expected value, right? The possibility will uh will what is called, like, okay. s- uh the main idea is that uh if there is a situation that the agent can have heavily punish or penalty here, but the possibility of that action is very low. The uh, and when compared to another situation where there is no penalty at all, but the reward is much lower than 200, so the expected value will uh, come out will be lower than this 138, right? So, the agent will has the tendency to pick uh, the situation where the expected value is much higher. So in some situation, he will take the risk for the higher earn. But now I will talk about the distributional perspective of reinforcement learning, so you can have clearer view.
Yeah, actually, you can understand that in traditional reinforcement learning method, it actually don't use distribution for learning in memory. So they will try to do something that make the memory, or actually in a supervised learning we call data, right?
Yeah.
More effective, because in reformer learning there are no stable data. Actually, the data in reformer learning are unstable, so they need some method that need to be used to make the data more efficient.
Uh, okay, so I can you talk a little bit about more about the idea of data, because the approach of distributional is uh, not about the whole idea of deal with the data problem, but it deal with I would say that in the moment ahead problem. It will provide a clear view for the agent of what action will bring it. Okay, so I will continue here. In here I have two formula. The first one is the traditional learning Bellman equation, which will take will take the expected value of Q value, and the below is the Z Bellman. In the paper they call it that, and in here they drop all the expected value, and the what is that value is the not a single value but an O distribution. It will be clearer in the image under here. And the p pi of z is a distributional return with the policy pi at the moment. And when it go with the the discount value, this distribution tend to swing to near the zero, and the distribution here is the variant, what is called. Okay, I will pass this. And when you add the reward can be positive or negative. The distribution or the distribution of return here will move from left to right, and the t of p here is the matching process when the what you have original is a whole distribution of the return, but to interpret it in a way that we can use, we will put it into grid. We discretize it into grid, and we mapping it into a simpler form. Okay. Here we break down the what equation actually do in the traditional reinforcement learning. We tend to take the expected value of the queue mark queue of action primal A, right? But here in Z bounding, we will take the distribution of all the expected value of the distribution of S prime and A prime. And the idea is quite simple, but this approach will bring for the agent a much richer data. And okay. Yes, that's correct. Okay. And about the conversion proof, in here I will not have a deep explanation about how we will prove this approach will converge at the end. But the idea of how to prove it is tackled by using the gamma contraction mapping with the Wasserton matrix. Wasserton matrix is a matrix to evaluate the distance between distribution, and what have been proven in the paper before that. They try to prove that there is an gamma which lie between 0 and 1, which will and this term gamma dw of z in z at the time of state t and action t will 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 larger than the distance of t at the time of g s sa and t gsa. Okay. Anyone have a question? Okay. If no, I will move to the next part. And after that idea, in the paper, they propose a new algorithm named C51, which is categorical DQN. Right here, you will see that in the normal traditional DQN, it we will have an image or some kind of data of the state at the moment, and it will go into the model. We will extract its feature, and the output will be the return which each action that we take, and the value here will be a vector. The vector will be the expect the value that we could predict at the time t. But in C51, in the first part, they will be similar, but it will change at the last layer. The last layer will be, as you can see here, is a matrix of softmax, and it will be the distribution of return for each action at the state t. Okay, and for the pseudocode of C51 here, I have highlight the difference in the training process of the algorithm that are different from the original DQN. So in the DQN, with the action DQN, we often have a parameter named epsilon, and we choose instead of sometimes if the random value is bigger, or some people prefer is smaller than epsilon, we will choose the action random. But in the C51, we will choose the action based on the output of the distribution action. And in the C51, some parameter like z mean and z max here is the highest and the lowest value of the return that we expected to receive in the environment we set up. So they will be the initial parameter. And here we will receive the the z value in our model. The C51 model will be the output of the last layer. In most model will be linear, and they will the output will be had a dimension of n action multiplied with the atom. Atom is how we discretize the distributional tool. And the 51 here is stand for the number of atoms that we will initialize in the algorithm here. And they have proved that no, in the run process, the run test process of the paper, that the number of 51 is have been run and proved that is one of the most stable atom number. So people usually choose 51 as their atom number in this algorithm. Okay, so the output of the model here will be the will be an value instead of distribution at the first, and then they will discretize them into they will index them the value, the output at first into the distribution of return, and the loss will be used is a cost entropy loss to calculate the distribution of the Bellman and the distribution of the predict model. And in the run test, it has been proven that at that time of 2017, the approach of distributional reinforcement learning of DQN have outperformed most of DQN approach. And the C51 DQN have been the new SOTA over the architecture of double DQN in 2017. But this position is not long after that. But this research also shows that distributional reinforcement learning is a potential approach that many researchers should look for it. But C51 is only one of the approaches that they use to interpret the idea behind how the agent, instead looking for the target this expected value, they will look into the distribution of return at one state. So there are two main approaches to illustrate the distribution. One approach is the C51 that we just have go through, that they will discretize the return value from the model into grid, so they can express the distribution of return in a simple way. Another approach that they will use the quantile function. The quantile function will output the distribution of the O of return of the return in the process. So this approach is tend to be much clearer approach than the approach of we discretize all the distribution. But this quantile function is have another advantage of instead of the approach of use regular regression the quantile function can use quantile regression, which will be a straightforward approach for the quantile function approach of distributional reinforcement learning. And some extra information that the as I do some research, the SOTA learning approach with the Atari benchmark is as I remember is rainbow uh, the rainbow model. The rainbow model is a model that combines seven advanced in reinforcement learning at that time, and distribution reinforcement learning ideas is one of the advanced that is used to beat all other algorithm at the Atari benchmark. And that is all of the seminar today. Thank you for listening, and now will be the time for question. Anyone have any question about today's topic? Uh, yes, it does increase uh, the computation cost, but it with the computation cost will rely on the last layer on only at the last layer of the model. So it's not a much a different from the traditional approach. Yes, the return here, as you can see, with will be denote at z uh, what uh, what they expect the reward will be in their simulation or in their problem. Okay. Uh, is there any more question? Not an array of reward is an more specifically it could be an array of possibility of reward, like here you have an interval of reward from z0 to z4, right? You have like 0 point, 1 point, 2 point, 3 point to 4 point. But what will give to you in here is that the possibility it will be like uh 0, 0.8, 0.2, 0.1 or something. It could be the possibility of what the reward it will likely to receive it the action. it it takes that action.
Actually, I feel softmax distribution is not too good in continuous action space. Can you tell me more about the DQN in continuous action space?
Okay. This by decrement in continuous action space is not included in this content. I will talk about it. So maybe we will talk about it at the end of this seminar. The idea of solving the continuous action space with decrement is like in another paper.
Yeah, because actually using the last output as the softmax function is pretty like the introduction in reinforcement learning in the reinforcement learning introduction book, right?
Right,
There one part that talk about the distribution output with softmax function, right?
right. Like in the real world, like most of the reinforcement learning problem is about control problem, and the control problem is real world. We never discrete problem, right? So it all about continuous, and to achieve the exactly control, they have to solve the continuous problem, and the most of the I and distribution no reinforcement learning is likely not be able to solve the continuous problem, but the continuous problem uh, they another approach that solve the uh, continuous problem with the output is with the structure of the network will be uh, a lot different from this for the continuous problem.
Okay, thank you.
Okay, if uh no one have any question about the today topic about distributional reinforcement learning, I will end the seminar here, and thank you for attending. Okay.